going to take a look at differentials. Let's take a function y that looks like 3x to the 5th minus 2x. And we know that if we take the derivative of y with respect to x, so dy by dx, we're going to get 15 times x to the 4th minus 2. So there's our derivative. Now, imagine what happens if we multiply both sides of this equation by the symbol dx. Then what we'll have here is a dy on the left, and we'll have 15x to the 4th minus 2 all times dx. So this is the first time where we've actually thought of dy and dx as quantities on their own. And these dy and dx, these are called differentials. So dy is the differential of y, dx is the differential of x. Differentials are really useful when we're looking at error. So let's try a little problem involving differentials. Let's say we look at a cube and we measure its side length. Okay, so this particular cube side length is measured to be 3.000 centimeters. Now, let's say that we know that the true side length is actually a little bit bigger. Maybe it's 3.018 centimeters. Let's see if we can estimate the error that we would make in calculating the volume. So that would be the error in calculating the volume of the cube. Well, first thing we can do here is try to organize some of the information that was given in the question. So first thing we see is this 3.000 centimeters. That's our measured value in the problem. So let's give this side length a name. Let's say maybe call the side length x. So the x value that we measured, 3.000 centimeters. Okay, so in this type of error problem, value of your variable is always your measured value. Now, we were told that the true side length is actually a little bit bigger. So a little bit of error was made in this problem. And in this context, it's a differential dx that's going to represent that error. So we can think of dx as the error in calculating our value of x. And the way that we calculate the error is always the true value minus the measured value. So we just have to remember to always do the subtraction in that order. In this case, our true value we were told was 3.018 centimeters. Subtract off the value that we measured. So our dx is 0.018, and that's still measured in centimeters. So we've got our measured value, and we've got our little bit of error here. And the question is asking us to estimate, so that's going to be an important word here, estimate the error in calculating the volume. So what the question is asking us for is the approximate error. Not the exact error, but just an estimate of the error. So the approximate error, and that approximate error again comes from a differential. So we would like the differential of v. All right, so we'll calculate that in a minute. First, before we can get into that calculation, we probably need a formula for v, and that was not given to us in the problem. So we'll just need to think a little bit about what we're doing. We're looking at a cube, and we're talking about the volume of that cube. So the volume is x cubed. That's something that we just need to come up with from the context of the problem. So it's a little bit easier to have this written down in front of us before we go to calculate dv. All right, so differential of v, if you find it easier, you could think about calculating dv by dx first, because we're familiar with how to calculate derivatives by now. So dv by dx is equal to 3x squared. Okay, you could do that as an intermediate step and then write down dv is equal to 3x squared dx. So with a little bit of practice, we should be able to just jump into dv and write that down quickly, but if you want to do some work over on the side, that's fine. All right, so there's our approximate error. We know what our x value is. That's our measured value in the problem. We know what dx is, so we're all ready to plug in. We got 3 times 3.000 squared, and then times our error in x. So that's 0.018. And we can grab a calculator and just work that out. Comes out to 0.486. And because we're talking about an error in the volume here, that's going to be measured in cubic centimeters. So 0.486 centimeters cubed. So that is the approximate error in calculating the volume, and we are done the problem. Our answer to the problem, that was our approximate error in V. And just as a little side note, because you might be wondering about this, the true error in calculating the volume would be written delta V. So whenever it's an exact calculation, we use this delta here. Delta V would be exactly the volume that you would get using an x value of 3.018, and then just subtract off the volume that you get from using the measured side length. So you could try this calculation on your calculator. You'd just be going, well, the true value of the volume of that cube would be 3.018 cubed minus our estimated, or I should say measured value. So the volume that comes from the measured x value would be 3.000 cubed. If we try this on our calculator, we're going to get a much messier number. Comes out to about 0.4889, and then we have many decimal places here. Okay, so a couple of comments here. First of all, dV is pretty close to delta V. And that's a good thing for us. dV was easy to calculate, and as long as this value here, or dx, is pretty small, dv and delta v are going to be pretty close to one another. So for most practical applications, using dv is fine. Calculating the approximate error is good enough. But now you might be asking, why do we use differentials in the first place? Because in this previous problem that we did, there's no motivation right now for not just using the true error. So delta V really wasn't that hard to calculate. And so we need to think a little bit more about this question of why the differential itself is really that useful. So to answer that question, let's try a different type of example. Okay, let's say we're given a function, and I'm going to stick with the same function that we had in our previous question. So we're still talking about the volume of a cube. Now, let's say someone tells us that the relative error in calculating the value of x is 0.7%. And the question is to find the relative error in V. Find the relative error in the volume. Okay, well, let's organize some of the information in the question. We're told about the relative error in x. So whenever we're talking about the relative error in a variable, by definition, that means the differential of the variable divided by the variable itself. So it's the error that you make in the measurement divided by the measured value, if you want to think of it that way. So we are told that dx over x is equal to 0.007, if I write that as a number. 0.7%, the same thing as 0.007. The question is asking us to find the relative error in v. Okay, so again, if we think about what relative error means, it is defined as the differential of your variable divided by the variable. So we want dv over v. Let's start with the denominator. Remember, v in our problem was given as x cubed, so we'll just throw that in the denominator here. And on top, we want the differential of v. So remember, the differential starts off looking just like your derivative. So it's like 3x squared, only we need a differential on the back here. So differential always has to have a differential in its expression. If you get confused about this step here, so looking at this part here, remember saying dv is equal to 3x squared dx, that's the same thing as just saying dv by dx is equal to 3x squared. So you can mentally imagine taking the derivative and then just bringing this dx up, multiplying both sides there by dx. Okay, so a little bit of cancellation now. We can cancel a factor of x squared from the numerator and the denominator. And what we get is 3 times dx over x. Well, remember at the beginning of the problem, we said the relative error in x was 0.7%. Remember, dx over x was 0.007. So bringing that value in here, 3 times 0.007 gives us 0.021. So the relative error in v, dv over v, we could give that as a percentage if we like, 2.1%. So the reason why differentials are so useful is that there is a nice predictable relationship between the relative error in x and the relative error in v. So if we look at the relative error in x, 0.7%, relative error in v, 2.1%, the relative error in the volume was exactly 3 times the relative error in our side length. Number 3 comes from the dimension of the object.